My name is Rebecca. Potentially some of you have seen me waving in a video. I'm the elder data scientist. I am very excited to have you all here today. Like I was saying, today's tutorial is on a topic that I think will be new for many people. It is about asynchronous inference. So what is asynchronous inference and what does it have to do with data science, and why is it something that we think you might want to know about as a data scientist or a data engineer, or maybe a machine learning engineer? So to get you thinking in the right kind of frame of mind, I want to take you with me to the fortune teller. So I'm going to put a link in the chat. So this link will take you to an online fortune teller application where you can get your fortune told. And so I'd like you to do that. I'd like you to go to this, this website, crystalballfree.com/prophecy, and get your fortune told. And then whatever answer you get, I'd like you to paste it into the chat so that we can see what your fortune is. And I'll give people maybe, I'm seeing a few answers popping up. So once you get your fortune, put it into the chat. And, I'll give people maybe 90 seconds here. And then I promise, tell you what this all has to do with the lecture today. I think Praneet might win. That's the best one so far that I've seen. Professionally, a unique opportunity may appear today. Remember to beware of appearances. Great one. Intuitions will remain the best guarantee for the good progress of your professional life. Another great one. Great one, Marcelo. Okay, so here is what that all has to do with what we're talking about today. So this little app, this prophecy generation tool, we can think about it like an inference system. And just kind of as a disclaimer, we didn't build that. That's somebody else's tool. And it's not actually doing predictions. I hate to tell you, it's just, randomly generating, prophecies. But if you sort of imagine, like, this is kind of how inference systems actually work, right? Most of them are synchronous. So most of the inference systems that you interact with every day are synchronous inference systems. The one that this prophecy generation thing is a synchronous inference system. And there's a couple of options for how you can do synchronous inference, right? So the fortune teller can be like a server. So it's running inside a live cluster and it responds to our requests when we ask it for fortunes, or it can sit behind like a scheduler. And it can work in batches. So every time, maybe a certain number of, like, let's say 50 requests come in for fortunes, it can process all of those 50 things in a batch and send out all of the prophecies, all 50 prophecies at once in a batch. And so we'll all get our fortunes told at once, but the first person to submit the request might have to wait for a while before their batch gets served. Another option is that the fortune teller could sit behind an API gateway, and the gateway could manage requests and responses that are coming through to do rate limiting and stuff like that. This is usually, when we call things serverless, that's like the serverless way to do the fortune teller, right? It's fully managed. It's usually the most expensive option. But there's a couple of options for these kind of synchronous inference systems. But all of those things sort of presume that it's easy to turn around a prediction pretty quickly, right? It's randomly generating a fortune, or it's kind of picking something quick. The model is not very complex, but all of us are starting to work with much more complex models, like large language models, generative AIs. These are things that often take a little bit longer to generate predictions. And that's okay, right? Especially if the predictions are going to be better, right? We'd rather them do a good job and take a little bit longer than to return something right away that's not a very good prediction. So if your prediction generation process is going to take longer than the typical like API timeout time for a synchronous API, that's when you need to start thinking about asynchronous inference. So with that introduction in mind, I'd like to introduce you to our speaker for today. Dr. Benjamin Bengfort is an expert in machine learning and distributed systems. So he's thought a lot about synchronous and asynchronous inference systems. He is an engineer turned tech founder. He has written multiple O'Reilly books. He's the faculty director for Georgetown University's data science certificate program. And my crystal ball says that we are in for a good time. So with that, I'd like to turn it over to you, Dr. Bengfort. We are excited for your talk today.
Thanks, Rebecca, and hello, everyone. Thank you so much for joining for the webinar today, where we're going to talk about data flows for real-time model inferencing or asynchronous inferencing. So I'm going to dive right in. This particular webinar is a follow-on from the Rethinking MLOps as Data Flows webinar, which we refer to as MLOps 101. So this is MLOps 201. And in MLOps 101, we talked about data flows being ideal for three main things when it comes to machine learning operations: reproducible training, asynchronous inferencing, monitoring, and triggers. And so today we're going to focus on the asynchronous inferencing part of that first class. Now, if you guys didn't manage to attend that webinar, then you can feel free to watch the recording of that particular webinar later on if you have a chance. And I stuck a little bit.ly link in here, bit.ly/RADL-MLOps101, and that will take you to the webinar for the previous session. But let's dive ahead with asynchronous inferencing. So the first thing I want to say is that there is going to be code today. There's going to be Python code today. We're going to do something called a code tour, where I'm going to walk you through actual production code that is running, and you'll see a little demo today. And that will be the primary focus of what we're doing. So I hope that no one drops out, because there won't be any code just right off the bat. But that is going to be the plan for today's webinar. But before we can get into the code, I think at the very least, we need to understand the requirements that led to the generation of this code, an architecture, and maybe a little bit more of the why of what we're doing. So I'm going to go over some slides first to do a little bit of an overview, to make it a little bit easier for us to understand the code in context. So the first thing that I want to re-mention is another anecdote from Chris Chapo, the Senior Vice President of Data Analytics at Gap. And he shared this story where one of Gap's early data science projects, which was intended to create size profiles and determining sort of the range of sizes and distributions that their stores needed to meet demand, was a successful data product that they got into production. But the way that they got this into production was the data science team handed the algorithm to some engineer, and I imagine that algorithm was written in R, Python, but the engineering team recoded it in Java, implemented it, and deployed it. And it was running for 4 years or 3.5 years before they realized that the recoding had broken the implementation, and that this model was giving incorrect size distributions because of the recoding effort. And that's not meant to be a scary story, but my personal takeaway, and I hope the takeaway that you guys all share, is that data science teams must be in charge of deploying and managing their models. I don't think that having an organization where data science teams throw models over the wall to the application team is a good way to go about MLOps or even product development that requires machine learning models, AI models, or any sort of data engineering or analytics. And so if we have to be in charge of deploying and managing those models to make sure that models are correct, they stay current, they stay up to date, then we do need some mechanism of interacting with the application team so that they can consume the data product that us data scientists are working on. Now, there is a slight issue with that, and that's that data science teams should be good at data engineering, data visualization, data analysis, model training, model diagnostics, statistics. There's a lot of things that we have to be good at. And so the question is, do we also have to get good at application development? And I think that's a perfectly fair question. And I will present to you guys right now the sort of standard way of model deployment that I've seen that exists in sort of the most common production ML tools or MLOps tools that use model registries, or even just in the data engineering teams that I've seen, is what they'll do is they'll create an internal microservice whose customers are meant to be the applications, right? And so what the data science team does is they create a Flask or Fast API Python API service that loads the model that they're working with. And that Flask or Fast API service receives incoming HTTP requests. Those requests have the feature data. It applies the feature data to the model to get an inference or a prediction, and then it sends a reply with that prediction and possibly some other information like confidence intervals, most informative features, that kind of stuff. This is what we refer to as a synchronous request response model. And what synchronous means here is that when the request comes in, whoever is making that request is going to be waiting until the model applies the inference to the features and can give you a response back, right? So that client is waiting the entire time. Now, a lot of models are not just single models, they're actually collections of models. And some models, particularly instance-based models, may take a quote unquote long time to make a response, right? And by a long time, I do mean, sub-second, right? We're still talking about, computing speeds here. However, when you consider that the sort of average latency for a database request is 10 to 20 milliseconds, and the average response time required for a web front end is 150 to 200 milliseconds, you can see that sub-second might still be 2 to 5 times longer than is good enough for the application team. And that can be a problem. And so stuff starts to happen, right? When you start to think about things in terms of a product like that. You've deployed your API as a microservice. You do have the potential to scale it by increasing the size of the deployment. But you, the data science team, become in charge of a lot of other concerns as well, right? Not only do you have to handle data storage, you have to deal with security and access. You have to deal with scaling the back end. You have to deal with tracing and observability at the application layer, such as logging, error handling, performance metrics. And all of these types of things stretch perhaps our definition of what a data science team should be doing in order to get a model into production. So I would like to propose an alternative way of thinking about our MLOps, and one that hopefully realigns these concerns to the more appropriate teams. And that is using an asynchronous inferencing model rather than a synchronous one, with a deployment that is structured on top of data flows rather than on services. And by doing that simple shift in our architecture, I think what we do is we redistribute concerns a little bit more effectively. The DevOps team gets back the security and scaling concerns. The data science and data engineering teams gets back the focus on model monitoring and making sure that the model is correct. And the application teams no longer have to worry about whatever the service model is that the data science team has provided, or whatever the API format or documentation is. So to introduce us to an asynchronous inferencing architecture, I'd like to introduce a simple one. And this is the architecture that I will be demoing in code later on today. Now, this is a simple architecture. This can get more and more complex. I know that a lot of organizations are running multiple microservices with multiple front ends and things, but let's just stick with this little architecture to start off with. So the first thing that we have is we're going to have our product app here on the left, right? And since everyone here is probably Python developers, we'll make this a Django web app. The Django web app is backed by a production database. And in this case, this database is Postgres. And on every web request, Django will create a response by loading information in from the database. Django is also useful for building APIs and all kinds of stuff, but it's really meant for much larger applications and something like Fast API or Flask. So what we'll do is, rather than Django connecting to some other microservice to get an inference when it wants to make one, instead, what Django will do is it'll publish its instance that it wants a prediction onto this instance's topic. And so this is where we get into data flows. So topics are data storage. It's a data storage abstraction that stores an ordered series of events. And these events can be anything. For the purposes of this conversation, we'll say that they're little snippets of JSON data with a little bit of metadata surrounding them. A lot of systems do eventing, Nats, Kafka, and others, but of course, we're going to be talking about Ensign and the Ensign streaming system for publishing these instances. So Django will publish this instance into the instance topic. We'll then create our model inferencing service, right? And this will be the part that the data science team is responsible for. So instead of creating an API, what we'll do is we'll create a Python process that runs, so it's still a service because it runs forever without quitting. And the job of this inferencing process is to subscribe to the instance's topic. And every time it sees an instance, it makes a prediction, and it publishes its prediction to the inferences topic, right? So now we have instances and inferences. And the reason that this is asynchronous is because Django no longer has to wait until the model inference is complete. It can publish the instance onto the topic, and then it's done, right? It's done. And that publishing process is, again, on the order of the tens of milliseconds, right? So your SLA, you don't have anything to worry about. The model inferencing handlers, they are just subscribing to this topic, and every time that they get a new inference, they just apply those predictions. And so if there's a sudden burst in load, the system is not going to slow down at all, because the instances topic will essentially act like a queue, holding all of this data, waiting for the inferences to be published. Now, we still need a mechanism to get the inferences back to Django, back to the application. And so what we're going to do is we're going to actually create an application side sync. The reason this is a sync spelled with an I instead of a Y, the idea is if you have a faucet with data flowing, it's flowing into the sink, right? That's the sort of final place that it goes. And so what this thing does is it subscribes to the inferences topic, And every time it sees an inference, it updates the row in the database with the inference. And the next time that Django makes a request, or someone makes a request to Django, and Django loads the database, it will have the prediction, and it can respond to the user with that prediction. So we have a question in the Q&A channel, what are topics? So topics are a data engineering abstraction. So you can think of a database table as a relational database abstraction. A topic is an abstraction for streaming or real-time databases. It's essentially a totally ordered collection of events that have been published into the topic. And then when you publish something into a topic, you are appending an event to the end of the topics list. And then what subscribers do is they read from the beginning of time to the end of the time, waiting for new events to come in. So the topic is a storage mechanism to store events as they're published. And you can think of it like a database table. It's just instead of rows, you have events. Okay, so this is the architecture, and we're going to explore exactly this architecture here in a second. But before we do, I want to talk about the benefits and the trade-offs of establishing such an architecture. So the first thing is it might be a bit more code at the beginning, right? So instead of creating a single API service, now you have to create this model inferencing handler, and you have to create this sync thing. So now you have a little bit more code to write at the beginning. However, I would say that for those of you who have written API services before, what you'll quickly realize is that as you grow your service over time, it's going to end up being far less code overall. So maybe a little bit more to start up, but in the long run, you're going to be saving yourself a lot of coding. Second, in this example, we just have one single application that is collecting inferences. But this no longer has to be the case with this inferences model. We can actually have something else subscribe to this inferences topic and do things like, pass them to human annotators for updating data sets or for doing model monitoring. Or perhaps we want an admin API that will tell us the sort of real-time percentages of the different classes and get an understanding of what our users are doing in the application. Those types of consumers can be added to this architecture without interrupting or even dealing with the original application. And one reason that's a really good thing is because often this database over here, that's where this information would be in the synchronous model. But this is your product application database. And you guys probably know that your DevOps teams are going to be really protective of this database, right? Because this is going to be the user's data here. And so they're probably not going to let you get direct access to this database. So by being able to subscribe to the inferences topic instead, now you've created data flows that allow you to get data to the right place in the right time and allow you to prototype more quickly, new features and new things far more easily than the sort of monolith architecture would allow you to do, or even just a general microservices architecture. Also, this is not unknown to your application development teams, right? This is actually a standard web application practice for requests that take more than dozens of milliseconds. So Django users are probably familiar with doing asynchronous tasks with Celery for sending emails and things like this. So this is not a big ask to re-architect for your application teams. And then there's some other benefits, right? Simpler application with agnostic documentation, whereas an API will have very strict documentation and error documentation. And you still get the same scale-up pattern that you would from the synchronous model. And finally, you don't need to store your inferences anywhere because they are stored in the data flow. They're stored inside of the topic. So there's a lot of good benefits. There are a couple of trade-offs, but I think there's a lot of good reasons to using this architecture for MLOps and to make sure that your models are being deployed and used in production. Now, I will say, those microservice perils that I mentioned before still exist, right? You still have security concerns. You still have observability, tracing, error handling, and logging concerns. You still have all those concerns. However, you are delegating those responsibilities away from the data science team and putting them in the hands of the DevOps team that manages the event bus, right? So the event bus is the application that makes those topics happen. And so in Rotational's case, the event bus is Ensign, right? Ensign is the thing that allows you to publish and subscribe to things. And the DevOps team can handle the security and observability on Ensign without the data science team needing to worry about that. And the application team still has all of its own security semantics and performance semantics that it needs. So you get to scale and maintain your models independently from those things. And I think that that allows us to collaborate much more effectively inside of our organizations. Okay, so let's get into some code with that introduction. Let's see exactly what this Django-based architecture looks like. So here is the little demo that I wrote. And what we are doing is we are deploying a fairly simple sentiment analysis model that was trained on US travel airline reviews. So this was a Kaggle data set. And we're going to assume our little front end wants to guess the polarity, whether it's a positive, negative, or neutral sentiment when you add the review. So here's the little demo of this Django app. Everyone cross your fingers that it still works. So let's say, we waited in line for hours. Everyone was miserable and the flight was still canceled. I didn't get any assistance from customer service, and we spent a horrible night on the floor of the airport. That's what airport, right? So I'm hoping this is a negative review. Now, this happened really fast, but what happened was exactly what we said in the architecture, right? I submitted this request. I'll just bring the architecture right back. So I submitted the request to Django. Django published that text into the instances topic. There was a modeling event handler in the backend, right, that was listening for that text. It applied the sentiment analysis to the text and then published that into this topic. Then we had this sync subscriber that was listening for that inference, and that saved it back into the database. And then that ended up appearing on the screen all at once. Now, I will say there was a little bit of magic that happened there, and that all happened really quick. These are real-time databases that are incredibly high performance. So from your perspective, I pressed the submit button and it happened. But that entire chain of events did just happen the way that I mentioned it. What this thing is doing, what this front end is doing, is it's making repeated requests to the back end to ask for updates, right? And that's why things updated so quickly. In fact, this says 1 minute ago. I want everyone to keep an eye out. I'm going to publish this again. And when it's seconds new, you'll see the seconds incrementing up. So let's try for a neutral polarity. So this is a question. So it says posted now, and then I'm not doing anything. I'm not clicking on anything, but in 5 seconds, hopefully it'll update to 5 seconds ago. Maybe. Oh, 16 seconds ago. Okay, so there was some delay on my front end, but this thing is, there it goes, 21 seconds ago. So there is a little thing in the back end that's sort of refreshing and making continual requests to the server so that we see all of these things update in real time. And that's the little application that we wrote from the front end. Okay, so let's dive in and see the code that makes this work. So like I mentioned before, what we're going to do is something called a code tour. And I hope that my screen is big enough so that everyone can read it. Now, code tours are something that we do at Rotational, and this is a way to sort of help our colleagues understand exactly what was written in the code outside of the scope that might be in a code review or something like that. So all of this code is in GitHub, so you guys have access to it. You can run this code using Docker Compose. We have some instructions about how to set that up in the README. So please feel free to access this code and use it and adapt it, fork it if you'd like. But it's under my GitHub, /sentiment reviews. And I will just quickly post that link into the chat so that you guys don't have to scramble to type that in or anything like that. There is a lot of code here, so I just want to give you, some quick organization. The first is the Django code. So the Django code is actually under app, reviews, and static, and this manage PY. That is all the Django code that's in this. And under static, there's actually the JavaScript for the app, which is managing the front end application that I said. Now, this webinar is not about Django. So if anyone's interested in Django, I can certainly point you to other resources. So we're going to be ignoring the Django components, which again are app, reviews, and static. Now, inside of the fixtures is this model.pickle. So that's actually the trained model that we're going to be using. And what I will say is that the model training is also beyond the scope of this webinar, right? But this text package here contains the NLTK data and some code for training the sentiment analysis model. And then there's this models.py. This is the script that engages the model training effort. So again, that is outside of the scope of this webinar because we're going to be looking specifically at the asynchronous inferencing workflows. But models.py and this text package is what trained the model, and the model itself is inside the fixtures folder. If you are interested in that sentiment analysis, there is a gist here that shows how to use NLTK to train a very simple text classifier. And of course, all of that code is in the repository. I'll put the link to that just there as well. And just so I can show you that there's nothing up my sleeve, I mentioned the model was trained on the Kaggle Twitter US airline sentiment data set. And the confusion matrix for the model that's in that fixtures library is here. So you can see that we have an overall F1 score of 0.7, where we have far more support for the negative class than we do for the neutral or the positive class. And so if you guys do use the Sentiment Reviews app and you run this, you'll probably see far more negative inferences than neutral or positive inferences. That was certainly my experience. But those are the F1 scores for that model that was trained here. So, and then last, there's this Docker Compose, Dockerfile, and Docker Ignore. Those things are what I've been using to deploy this model, because there's actually several processes that have to be running in this architecture. There's the Postgres database itself, there's the Django application, there's the model inferencing handler, and then there's the sync subscriber. So you have to run all of those things simultaneously. And I find that it's easier to use Docker Compose to describe those services rather than try to open up a bunch of terminal windows and run things in a bunch of terminal windows. So when you guys look at how to do this yourself, the first thing you have to do is create an account on rotational.app. You'll want to create a project with 2 topics and get some API keys, save those to a .env in your local repository, and then so long as you have Docker and Docker Compose installed, you can use this, Docker Compose profile all build, Docker Compose profile up, and then when you open a web window at localhost 8000, you should be able to see this little application that you can then run predictions on. And in your console, you will see all of the logging with, instance 52 received, instance 52 inference and save database. You'll see all of the logging workflow there. Okay, so that was the code tour. So let's look at exactly the code that is used to run the model inferencing asynchronously and the sync code. And that's inside this file called sentiment.py. So this is where all of the code for this webinar that is of interest is. And I will just quickly take us through this code. I'm going to make this a little bigger, just maybe so it's a little bit more readable. So the first thing is that when you guys are writing code to do model deployment, you need to create what's called a service, right? This is a piece of code that is a long-running process, right? It's something that you start and it runs forever. When you're creating services, I strongly recommend that you use argparse to create a command line application so that it's much easier to be able to do like /sentiment.py -- help, and you get some information. So this argparse command is defined down here in the if main, and we basically have two commands. You can run predict, which is the inferencing loop, or you can run sync, which is the inference sync handler. So these two commands are defined in the predict and sync functions, respectively. I also want to point out real quick that the PyEnsign API, which is the API that we're using for this example, is using the async.io code for asynchronous coroutines. And asynchronous coroutines are an alternative to threading and multiprocessing for being able to do concurrent work in Python. So in order to have a long-running process that runs forever and doesn't stop, we're going to use this async.io.run function. Async.io is part of the Python standard library. And we're going to run either the predict func, right? So that's in args.func here, or we're going to run the sync func. And there will be a loop that just continuously loops over a subscription to a topic and doesn't quit unless you type in Control-C or something like that to kill it. And that's what this async.io run is doing. If you are not familiar with async, there is another webinar coming up 3 weeks from today, where we'll talk about the basics of PubSub, and I think that webinar will get into asynchronous code as well. So let's take a look at the code that is required to make predictions, right? And this code is about 42 lines of code long, so it's very digestible here. So the first thing that I'm doing is I'm opening that model.pickle file that's in the fixtures directory, and I'm loading it with pickle, right? So I think most of us know that when we train a model, we can save that model to disk, particularly if it's a scikit-learn model, using pickle, and then we can load that model into another process in order to make inferences. So here is where we're loading our saved model as a pickle file from disk. So what this model is it's a scikit-learn pipeline that includes the feature extraction methodology, as well as the underlying classifier, which is a logistic regression, which is kind of a standard classifier that's used for sentiment analysis. Then we're getting from the environment the names of our topics. So what's the name of the instances topic, and what's the name of the inference topic? And then we are going to establish a connection to Ensign. So this Ensign function here, which has been imported, which I've defined up here, is an asynchronous function where we create an Ensign client, passing in our client ID and our client secret. We can then make a status request to check to make sure that we've successfully connected to Ensign, print the version of Ensign that we're connected to, And then we can loop through our topics and make sure that the topics exist. And if they don't exist, then we'll raise an exception, this runtime error, because we can't do anything if the topic doesn't exist. So this Ensign function is a little helper code, this async def Ensign, to connect to Ensign, perform a status check, and make sure all of the topics exist. And you'll see this is very common kind of pattern in pub sub or streaming code, where you make a connection, make sure the topics exist, ping the server, make sure that you're good to go. So back in predict, we've now awaited the connection to our Ensign client. And so once that's done, now we have our Ensign client that we can make requests on to the Ensign server. So what we need is a loop that runs forever. And so what we're going to do is we're going to use this async for event in client.subscribe instances. So client.subscribe is creating a subscription onto the instance's topic. And this async for is going to loop forever, waiting for events to come from that topic. So you can think about this process just sitting there, listening for the topic. And right now, it's not doing anything, right? It's just waiting for the next event. And then when someone types into the reviews app and Django publishes that instance event, then that's going to come into this loop as an event. We're going to do all this work. And then once we're done, we're going to go on and wait for the next event. Where is the data pre-processing happening in the predict method? So yes, I haven't gotten to that quite yet, but the model itself is a pipeline that has feature extraction mechanisms first, and then the classifier at the bottom of the pipeline. So one principle of deploying models is you want to create pipelines that do as much feature transformation as possible so that your expected input is as raw as possible coming in. So the model does do tokenization, part of speech tagging. It does vectorizing using TF-IDF, I think, and then that data is passed into the predict method, which we will see shortly here. So once we get the event, we load the event data from JSON, because that's what we're publishing is JSON. And then we create our inference that we're going to publish once we have made that inference on the event. Then we can use the model to perform a prediction on the instance. And note that there's a lot of an array things happening here. These array things are happening because scikit-learn models expect an array of feature instances, not a single instance. So to predict a single instance, you have to put your instance inside of a list and then get the first element out of that list. So that is going to return a class, either positive, negative, or neutral. And then we can also use the decision function of the logistic regression to get the confidence, where a high confidence is a good confidence that the model really thinks that it got the right thing, and a low confidence says that the model is unsure about the prediction that it made. So that's it. Here we've gotten the instance from the event instances topic, and we've made a prediction on it. So now that we've made that prediction, we want to publish that prediction onto the inferences topic so that our sync can get a hold of it. So what we're going to do is we're going to create an event. This event is a class that I've imported from PyEnsign up here. I'm going to dump some JSON data of this inference dictionary into the data, and then there's a little bit of boilerplate here code saying that the MIME type is application JSON. I'm using the schema name inference with a schema version, and then I'm adding some metadata, which is just a dictionary. In this case, I'm adding the ID of the review as metadata. Then I can publish that out event onto the inferences topic, and I can wait for the server to say, check, it's been published, before I print, we've inferenced, and then we go back to the top of this loop. So that's it. And when you look at this code, These lines of code right here replace all of the API boilerplate code that you might have to write for Fast API or Flask. But all of this is the same, right? This is what your handler would be doing if you were writing a synchronous API. And rather than having sort of an event, you would probably just write JSON out into the event stream. So we have another question. In large deployments to save on resource usage and for scaling in cloud environments, could the long-running services be replaced with functions that run only when invoked, e.g. when an event is received, e.g. Serverless functions? That is a wonderful question, Jennifer, and the answer is yes, that is possible. On our roadmap at Rotate, what you need is you need some way to get the event into the serverless function. So if you're using AWS Lambda or Cloud Run or Azure Serverless or something, you need to have something listening to these topics and then calling the Lambda. On our roadmap is a hook to make this happen with AWS Lambda in the near future. But no matter what system you're using, you need that hook, that sort of connection between AWS and your eventing system. And I personally don't know if other tools like Kafka or Nats have those things. I assume that the cloud-specific providers like Google PubSub or Amazon SQS probably have those things. But again, I don't know for sure. So in principle, the answer is yes, you can use serverless for this. But you do need a little bit of additional code in order to make that happen. All right, so to wrap this up, let's look at the sync function, which is down here. And again, this sync function is just another 20 lines of code. So we're not talking about huge amounts of code to make this happen. So here, we're going to connect to a Postgres database. That's the Django database. So this function is more probably the application developer's responsibility than the data scientist's responsibility, because they're going to have access to their application database that they connect to. Then they're going to get the inferences topic name from the environment, and they're going to connect to Ensign. And then they're going to have the same event loop here, right? They're going to wait for inferences to come on the inferences channel. And when they do, they're going to load that event data, which again, that's the same data that we dumped out here. And they are going to create a Postgres transaction, and they're going to execute this update request, right? So they're going to update the reviews table. They're going to set the polarity and confidence to what we inferenced, where the ID is equal to the ID of the review that was inferenced on. And then it's going to wait, or then it's going to act like this was handled. It's good, we've got this inference. We don't need to see it anymore. And that's it, right? And so this little 163 line file, sentiment.py, which has things like argparse and helper functions, does everything from making predictions and loading the model and doing asynchronous inferencing to saving those inferences back down to the database. And so hopefully this gives you a good idea of how relatively easy it is to set up an asynchronous inferencing pipeline using something like Ensign. The last thing I want to show everyone is that you do have to have this event bus architecture set up to use this, right? There is a data system that's backing up all of this code that I showed. And for us, that system is Ensign. So if you guys are using Ensign, which you guys can totally use for free, you would go to rotational.app, you would create an account, and once you get to the dashboard, you'll get somewhere like this. And you'll create a project, right? So I have a project already created called MLOps with a description that's here. And then once you're in your project, you're going to have to create two topics, right? You're going to have to create a topic called instances, and then another topic called Inferences. And you can see I have these things set up here. And then finally, you're going to want to create API keys. I recommend just creating a full access API key. You'll download the client keys and then follow the instructions on the GitHub README for how to put where to put those keys in your environment so that you can run this. But those keys are used here, right? The client ID and the client secret, they're loaded from the environment here using the .m file. And then the names of those topics that you created go here. They're loaded from the environment here. And again, that's just editing the .env file in order to make that happen. So that's what you have to do to set things up. But you can go into your topic and you can see that this topic has 28 inference events inside of it. And we can even look at those events. So I'm going to do a little SQL query here. And I'm going to select everything from the inferences topic. I'm going to offset it 20 so that we can see the last 8 events here. And so you can see this is the data that's inside of that inferences database, right? This is all of that JSON data that we were publishing. And we have the polarity, we have the confidence, and we have the ID of the review, right? So this is all of those inferences that we published, or at least the last 8 inferences that we published to this topic. That you can see, review number 52 is here. And if we look at the topic, this is the inference for review number 52, neutral with a confidence of 2.22, right? Which is, in fact, what we saw here. I can back out of this and I can go to the instances table and we can do the same thing. There's been 51 instances published, and the reason there are more instances published than inferences is because I was debugging, building this application, trying to get the model to work and everything to work. But we can do the same thing. We can offset, say, 45, limit 10, so that we can see the last 6 events or so. And I'll go all the way to the end here, and here's the text, right? This is a question ID 52. Right, so this is there's nothing up my sleeve, right? Because you can see the exact timestamp. You guys were on the call when I made this publication. In fact, it might not hurt to do another positive review here. So let's try. This was a very informative webinar, and I enjoyed it immensely. I can think this is probably going to be negative polarity. Oh, it was positive. Great. Going back to our topic tab, we can run the query again and go to the end. And you can see this was a very informative webinar and I enjoyed it immensely. It's in the instances. And if I go back to the inferences topic, again, this is just there's nothing up my sleeve, even though this appeared to happen lightning fast. That entire data flow that we just showed you is what's happening here. And then I'll go to the end of this query. And here's our positive inference on ID 53 with not such a high confidence. It's not terribly sure that this is a positive polarity, but there it is. So in conclusion, I know that we're at the end of this. I think that in order to start thinking about real-time applications and the next generation of ML and AI applications that are going to be handling large data loads, I think it's important for us to, as a community, to start rethinking MLOps as data flows. There's a lot of specialized tools out there now for time series database, time series inferencing, neural network modeling and things. And those are all good tools to have, but we need to be able to get the data to the right place at the right time. And so the more that we start to rethink the MLOps more generally as data flows, the more effective that we'll be as data science teams about getting our models into deployed and into applications. Particularly thinking about things like reproducible training, asynchronous inferencing, which we talked about today, and monitoring and triggers. I suspect that if you guys are interested in a webinar specifically on reproducible training and monitoring and triggers for retraining, if you guys are interested in those topics, please let us know, and we'd be happy to host a webinar on those topics as well. For now, what I would like to invite you guys to do is to try to deploy your model on Ensign, right? Hopefully you saw that it wasn't a huge amount of code to do it. So we invite you to explore and experiment. We have a data playground if you're looking for a real-time data source. And if you do get your model deployed, send us a link and we'll send you a t-shirt and a sticker. And of course, we are always available for any questions that you might have at support@rotational.io. So with that, I will hand it back over to Rebecca to conclude.
Thank you so much, Benjamin. That was wonderful. Great demo. Really fascinating to see sentiment analysis in action. I think that that's all we've got for today. If there's any little questions, we can hang out for another minute or two and people can put questions in the chat. But otherwise, we hope that we will see you at the next one.
Thank you, everyone.
All right, I don't see any more questions, so I think we can wrap up. Thank you again to our speaker for today, Dr. Bengfort. And hopefully we will hear from you soon if you play around with the code here that you saw today or potentially in the next webinar. But thanks again for joining today. See you next time.